Hello everyone, welcome to Curious Calculations. In today's session, we are dividing into an interesting topic from the number system, irrational numbers. Let's explore what makes a number irrational and how they differ from rational numbers. So we can start from the definition of irrational numbers. So what is an irrational number? A number S is called irrational if it cannot be written in the form P by Q, where P and Q are integers and Q not equal to 0. So here it is saying that a number S which cannot be written in the form of P by Q, where P and Q are integers and Q not equal to 0. And we know if a number R equal to a rational, we can written in the form of P by Q and Q not equal to 0. So this is the case of rational, this is the case of irrational. We cannot write in the form of fraction. For example, we know pi, then root 2, root 3, root 5. Any number comes in the under root except the perfect square numbers. We can say they all are irrational. What I said? Except the number perfect square. If I am taking 16, square root of 16, we have the value 4. But this is rational. Okay. And the remaining numbers, okay, except the perfect squares, comes under the square root. We can say they all are irrational. Okay. Now, coming to real numbers. So, this is the final set of number system. Okay, real numbers. What is mean by real numbers? Real number is the collection of all rationals and irrationals. Real numbers. It is the collection of all rationals and irrationals. Okay, so we already learned that every number can be represented a unique point on the number line. Similarly, we can say every real number is represented by a unique point on the number line. Okay, so here is a number line. We are marking 0, 1, 2, 3, etc. Similarly, -1, -2 on the number line. So it not only these numbers, we can mark any point. Okay, if it is 22 by 7, okay, it is 3 point something. So we can mark here. So any real number we can mark on the number line. And in the second term also every point on the number line represents a unique real number. Okay, so from this if you are taking one point, it is a represents a real number. Okay, so if you are taking any point on the number line, it's represent a real number. Let us discuss exercise 1.2. State whether the following are true or false. Justify your answer. So you have to say that the given statement is true or false. Every irrational number is a real number. So we discussed that real numbers are made up of rationals and irrationals. So what is asking here is every irrational is a real number. So what we can say? Yes, it is. Because what is the reason? Justify your answer. Because collection of, we can write the definition of real number, because collection of all real numbers are made up of rationals and irrationals. Clear? Then coming to question number 2. Every point on the number line is of the form root n, where m is a natural number. So every point on the number line is of the form root n. So you just think about the negative number. So what we can say is negative m is possible? So no. So what we can say? No, because no negative number can be the square root of any natural number. Any natural number. Then last one. Every real number is a irrational number. Asking the converse. Every real number is a irrational number. Converse is not true. So no. So what we can say? Answer is false. Actually we want to write true or false. No. So here true. Here it is false. Okay, no problem, whatever it is. So here we can write false. So to show it is false, we have to show one example. Every real number. You can choose a real number which is not irrational. So we can say the number 5. Okay. So 5 is a real number but not irrational. Clear? Then question number 2. Are the square roots of all positive integers irrational? If not, give an example of the square root of a number is a rational. So what it is asking, are the square root of all positive integers irrational? In the beginning I told that square root of 16. What is square root of 16? It is 4. So if not, give an example of the square root of a number is a rational. So example is this one. You can take a perfect square number in the square root of the square root. So we get the answer a rational number. Okay. So not only this one, you can choose number root 4. It is equal to 2. Any perfect square you can take. So it comes a rational. Clear? Coming to the next topic, real numbers and their decimal expansion. Here I had shown 3 fractions and their decimal expansion. The first one is 10 by 3, and second one is 7 by 8, and the third one is 1 by 7. Here you can see their decimal expansion. Okay, so look at the quotient and also the remainder. Okay, so what in the case of first, what we can say in 10 by 3, look at the reminders. Here the remainder 1 is repeating. Okay, so the quotient is also the same values. And what about the second case, 7 by 8? After a certain stage, the remainder become 0. Then 1 by 7. Look at here. Here we get the remainder 3, 2, 6, 4, 5, and again starting from 1. So after a certain stage, again it is repeating. Okay, have you noticed this one? So we can say decimal expansion of such fractions are terminating and non-terminating. Okay, so terminating means the remainder is 0. We get after a certain stage, we get the remainder as 0. So example is 7 by 8. Okay, so we can say this is a rational. Okay, so according to the decimal expansion also we can say the numbers are rational or irrational. So if it is terminating decimals, we can say the numbers are rational. Then coming to non-terminating. So non-terminating means it is two types. One is recurring and other is non-recurring. Okay. So recurring means repeating. Okay. Recurring means repeating and non-recurring means non-repeating. Okay, so non-terminating, repeating. So what from these A and C are the examples, 1 by 7 and 10 by 3. Both are repeating. You can see here 10 by 3. What happening? The number after these decimals are 3 is repeating. Okay, continuously repeating. And what about here? After this 6 times again it's starting. Okay, again it will repeating. Okay, so it is repeating or recurring. Okay, so we can say non-terminating recurring decimals are also called rationals. Okay, and the decimal expansion of the form non-terminating, non-recurring. For example, 1.01001, 0001, 00001, etc. We can say here the numbers are not repeating. You can see the numbers 0 and 1 are there, but after 1 0 the number 1, then after 2 0 the number 1, after 3 0, so the numbers are not repeating. Okay, so we can say the non-terminating, non-recurring means it is irrational numbers. Okay, so questions will comes according to this, that the given decimal expansion is rational or irrational. So you have to check whether they are repeating or terminating. Okay, so depends upon that we can classify into rationals and irrationals. So if you found this explanation helpful, don't forget to like this video and subscribe to Curious Calculation for more such explorations. And if you have any doubts or suggestions, drop them into the comments below. Thank you for watching. Keep exploring the wonders of maths. See you in the next video. Thank you.